Right, hi. So yeah, I'm Sophie Taylor, and I'm a PhD student working on mathematical uh, frameworks for cognition, specifically focusing on category theory. So I'll just start with a bit of quick background. Symbolic cognitive architectures, they are what are referred to when people talk about good old-fashioned AI. And they're essentially just production systems with an attitude, and pun intended. But here it's symbolic doesn't necessarily mean working with like primitive atoms in the style of like nominal set theory, rather just symbolic logic. This could be the internal logic of a category, for example. So here's an example of a cognitive architecture based on the Saw architecture. It's similar to a multi-tape, multi-head Turing machine. The blue boxes are long-term memory, essentially databases. The long-term memory isn't necessarily separated like shown here. The red lines indicate data flow, the orange lines are control signals, and the cross-hatched boxes are fixed functionality but can have tuning knobs exposed to the working memory. So since we're dealing with production systems, let's talk about how to do rewriting categorically. So this is done by double push-out rewriting. Double push-out rewriting is a categorical approach to describing and applying rewrite rules where rules are specified as a span. In this case, the objects L, K, and R, along with the morphisms L and R. The central object, K, specifies the common interface between the left and right-hand sides of the rule. That is to say, the structure that remains the same during rewriting. The actual rewriting is by virtue of horizontally gluing two push-out diagrams together. With the rule span at the top, the bottom left object is a matching object, and the bottom right object is the rewritten result. DPO rewriting can be done in any adhesive category, which is a category where push-outs and monomorphisms play nicely together in essentially the same way they do in the category of sets. Another thing to consider are double categories. These are most easily defined as internal categories in the category of categories, which is a bit of a mouthful, but it's much more fruitful for our purposes to think of them as being categories with three classes of arrows. Vertical arrows, which are ordinary category theory morphisms, horizontal arrows, which intuitively describes how two objects relate, and squares, which describe how horizontal and vertical arrows interact. Further, all of these morphisms have the obvious composition laws. One example is the double category of relations. The objects are sets, the vertical morphisms are functions, the horizontal morphisms are relations, and the squares essentially expressing coherence between the two. Another example is the double category of profunctors. This has categories for objects, functors for vertical arrows, profunctors for horizontal arrows, and natural transformations for squares. Virtual double categories generalize the composition on the horizontal arrows in the same way multi-categories generalize monoidal categories. In a virtual double category, the horizontal arrows do not have to compose, nor does there have to be a horizontal identity arrow on an object. What this then means is that the squares in a vertical double category can take arbitrary length sequences of horizontal arrows as input. This means we can form virtual double categories more often than double categories, and also gives us more flexibility when designing a virtual double category. Here we'll focus on double categories which form pro-arrow equipments. These are double categories where the horizontal arrows behave like relations on sets or profunctors. Naturally, this means the two prior examples are both equipments. So it turns out that production systems with learning form a virtual double category with equipment. What does this look like? Well, the vertical arrows are changes to working memory, graph morphisms, for example. The horizontal arrows, on the other hand, give us the set of possible rewrites to get from one working memory state to another. By possible, what I mean is rewrites which the production system actually knows about and is allowed to perform in the current state. The two cells then correspond to learning by chunking, that is, learning new production rules by looking at the result of a sequence of applications of production rules. Let's consider how to actually construct the set of possible rewrites. In a symbolic cognitive architecture, this boils down to the problem of recognizing valid rewrite rules in some graph-like structure. Clearly, we don't want to include every span because not every pair of edges in a graph with a common origin will be a rewrite rule that we want to apply. One way to do this is to work with pointed graphs, graphs with a specified base node. We shall say then that a span is a rewrite rule if, and only if, there's an edge from the base point to the apex of the span. We can actually generalize this a bit by declaring a span a rewrite rule if it is reachable from a path that begins with some specified path, which itself begins with the base node. Of course, morphisms of working memory would have to preserve the base node and path. What's nice is that this point and path access method seems to be amenable to a description by profunctor optics, which is a framework for bidirectional data access and computation. So we now we have our production system described in a way to get the set of valid rewrite rules to transform one memory state into another. Let's consider how to actually get some dynamic behavior. Our problem is this. Given the current state of working memory, we want to pick a rewrite rule and apply it. Well, we know how to apply it by double push-out rewriting. We want a way to categorically collect all the rewrite rules that apply in the current situation. What do we have? Well, each horizontal arrow gives a set of possible rewrites. From this, we can get to the set of possible rewrites in a number of ways. One efficient way is to use what's known as a rete network, which is what I'm currently working on categorifying. Another way, at least when the double category is locally small with respect to the horizontal arrows, is essentially summing over all of the sets of the horizontal arrows whose source is the current state of working memory. This could be extended to a contravariant functor, that is a pre-sheaf. What's interesting is that this functor can be interpreted quite straightforwardly as giving a set of possible cognitive worlds in the sense of crypt key semantics for modal logic. If we follow this cognition is a functor line of thought, what can that bring us? Let's look at change of base functors. These are functors which change the object you slice over in a slice category. They also have two very interesting adjoint functors, the dependent sum type and the dependent product type. We can get base change functors in a number of ways, as they are essentially what characterize locally Cartesian closed categories. If our category is a topos, or more generally, if it's fibered somehow. Well, we have a way to get a pre-sheaf from our production system. What if we consider the category of pre-sheaves of the horizontal category of our production system? Well, then we have a topos. From this, we immediately get a wide array of powerful tools, but one thing that stands out is that we get the full power of modal dependent type theory as the internal language of our topos. Let's consider another style of functor, learners. Learners are just what they sound like. They are functors which can characterize learning. The nice thing about learners for our purposes is that they fit in snugly to the framework of profunctor optics, keeping to the common theme of equipment and pro-arrows. Learners have a parameterization. One way to parameterize them is to use a rete network. Finally, let's examine what all this means in a broader context. Double categories are merely categories internal to the category of categories. This allows you to do a lot, but not enough to do all of category theory internally. This led to the development of pro-hour equipments. What we have been doing looks a lot like doing internal quiver theory. Is cognition merely internal quiver theory in some special category? And we haven't talked much about what we are rewriting, though. Standard approaches such as the subject, verb, object, and identity attribute value representations of knowledge graphs suggest an object-oriented description of knowledge. Well, let us consider processes acting on data and representations of them as string diagrams. After all, a lot of what we think about is not data, but the dynamics of data and the effects of various processes acting upon it and transforming it. We can also represent data itself with string diagrams, either as scalars in the underlying monoidal category or as processes applied to the identity object. So why not take string diagrams as the fundamental building block that our production system will operate on? There's a major class of string diagrams which represent many common processes that we encounter, which is based on commutative Frobenius algebras. An interesting thing about this class of string diagrams is that its syntactic category is 2-cob, a category of two-dimensional cobordisms. What makes this interesting in our case? Well, 2-cob also happens to be the syntactic category for two-dimensional topological quantum field theories. This suggests that the quantum-y aspects of cognition are merely a mathematical coincidence. It is the Frobenius algebras underlying string diagrams which are relevant, and not anything inherently to do with quantum mechanics. Yeah, that's it.